to today's class. It is chemical bonding, chemistry, higher secondary first year, and today's class is the last portion of chemical molecular orbital theory, the smallest unit of the chemical bonding, and it is a very important for entrance as well as class exam point of view. And almost each and every competitive exam, the question is very often asked from this one, and minutely follow this one. And this chemical bonding, that is molecular orbital theory, is based on some theory. And first of all, you must know the theories of the molecular orbital theory, otherwise you can't understand. A lot of questions from the theory also are being used or very often being asked from this topic. So first of all, let me explain what is molecular orbital theory and who proposed this molecular orbital theory concept. It was first proposed by Horns and molecules. And what are the theories? And these theories are very important, very often questions in the form of the statement true and false, very often asked from this one, and this is the backbone of this molecular orbital theory. Diagram is needed, and molecular orbiting theories are very important. Molecular orbital theories. Let me first explain. Out of all the theories or postulates, some of the theories 1 to 5, rest number 12s are theories as are there. Out of this, I am explaining 5. First of all, when two atomic orbitals combine, loses their identity formed molecular orbital. Say atom A and atom A combines, or maybe A and B different type combines to give A2. This is atoms, and this atoms has orbital is called atomic orbital. When these two atomic orbital combine, it gives molecular orbital A2. So here it is told that when two atomic orbitals combine, when any two atomic orbital combine, the atomic orbital loses its identity. This identity, after combination, it loses its identity, and it gives rise what is called molecular orbital. Am I right? First postulate. Second postulate, in terms of probability distribution, means probability of finding electron in the space around the nucleus is called probability distribution. In terms of probability distribution, the molecular orbital has electron probability distribution around groups of nuclei. That molecular orbital consists of two molecules, A, and this two has two nuclei, A and the electron probability distribution is around the two nuclei. But just as the electron probability distribution is around one nuclei of atom, here electron probability distribution is around one nuclei of atom. Here electron probability distribution is around two nuclei, means electron distribution around group of nuclei in molecular orbital. It is just the same as the probability distributions around the single atoms. Number 2, only those atomic orbital combines which have comparable energies, almost same energy. A bit difference in atomic energy and huge difference of energy may not be possible to give you molecular orbital. When these two has a comparable energy, then these two atomic orbital has the probability of combination to give you molecular orbital. Means they have almost same or a bit difference in energy, in terms of energy. Then these two atomic orbital may combine to give you molecular orbital. Number 3, only those atomic orbital, yes. Number 4, number of atomic orbital is equal to number of molecules. Very important one, very often asked in exam. If there are two atomic orbitals combined, it will give you two molecular orbital. If 3, it will give 3. If 4 atomic orbital combined, it will give you 4 molecular orbital. So number of molecular orbital is equal to number of atomic orbital combines. Number 5, two number of atoms combines to give, so atomic orbital, two numbers of atomic orbital when combines, it gives 2 molecular orbitals. Am I right? And these 2 molecular orbitals are 2 types. Its name is, one is bonding molecular orbital, other is anti-bonding molecular orbital. This is number 5. The theory, point number 6, bonding molecular orbital has lower energy and more stability. When I will show you the diagram, you will understand bonding is the lower one and anti-bonding is the upper one. In terms of energy, bonding has the lower energy, and in terms of energy, anti-bonding has the higher energy. And we know the bonding molecular orbital, since it has lower energy, it has more stability. Lower energy is the more stability and higher energy is the low stability. So bonding molecular orbital has lower energy and it has got more stability than the anti-bonding, which has higher energy. Next point is molecular orbitals. There are 2 types of atomic orbitals when combined gives you molecular orbital, and molecular orbitals are 2 types. One is bonding molecular orbital, another is anti-bonding molecular orbital. Bonding molecular orbitals are called sigma and pi, and anti-bonding molecular orbitals are called sigma star and pi star. When I will draw the figure, you will understand in better way. Next one, electrons are filled up in the molecular orbital in terms of the above principle, Hund's rule and Pauli's exclusion principle. This is the principle already we have explained in the first part of the chapter. In the structures of atom, we have already explained. So electrons are filled up in accordance of these rules. And number 9 is very important. We can very easily find out the bond order, and the formula of bond order is number of bonding electron minus number of anti-bonding electrons. We can calculate for the molecular orbital configuration. We will show you how to write, and I will show you the shortcut, divided by 2. And another one is, along with the bond order, we can also draw a lot of inference from the bond order. Bond order is directly proportional to the stability. If the bond order is more, the stability is the more. And if the stability is more, then bond energy is more. And if bond energy is more, bond length is less. Since, say, it is single. So, single bond. Another is double bond. Other is triple bond. So, the bond order has been increases. At the single bond, double bond, triple bond, bond order, bond multiplicity increases, means bond order increases. So along with the bond order, you will get the stability increases. Along with the stability, you will get bond energy increases. To split up this bond, energy will be required high. And when from single bond, double bond, triple bond, you will see the bond length will decrease. So you will find bond order is directly proportional to the stability. More is the stability, more is the bond order, more is the stability, more is the bond energy, and less is the bond length. More is the bond order, less is the bond length. Next one, with the help of this molecular orbital configuration, we can find out whether the compound or the molecule is paramagnetic, diamagnetic, more paramagnetic, less paramagnetic, and diamagnetic. So it is a very vital point, the topic molecular orbital theory, with the help of which we can find out the molecular or antibonding and bonding regarding the informations of antibonding molecular orbital, bonding molecular orbital. Also we can find out the bond order, whether it is single or double or triple. Well, also we can find out the stability with the help of bond order. Also we can find out in terms of bond energy, which has bond and less energy, which has more energy. Also we can tell which one has more bond length, which one has less bond length. Also we can find out which one is strongly paramagnetic, which one is weakly paramagnetic, and which one is diamagnetic. If in the structure, if anywhere we found a unpaired electron, that gives rise to fact that it will be attracted by the magnet, then it will be paramagnetic. and if the more is the number of the unpaired electron, more will be paramagnetic. So highly paramagnetic, less paramagnetic depends upon number of the unpaired electron. And if there are no unpaired electron in the molecular orbital structure, when we will draw, we will say that it is not at all attracted by the magnet, it is diamagnetic. So a lot of information can be drawn out, or we can get conclusion from the molecular orbital theory. Let us first up show how we can draw the molecular orbital structure of a molecule, and then with the help of this we can draw all the inferences or the explanations from the electronic configuration after doing the figure. From this configuration, molecular orbital theory, out of this we will write the electron configuration just to have written 1s, 2s, 2p, thrices, and this will be written in sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. In each and every question you will be asked, you will required to draw the electronic configuration in terms of molecular orbital concept, and this is a bit hard, and very often you will find it difficult to write this configuration in terms of molecular orbital without drawing the figure. So here I have drawn a figure to show, to explain, when atomic number is greater than 7 means oxygen onward, O and O. If it is O, atomic orbital, this to give you combined molecular orbital, this is O2. Say it is O, and this gives you O2, and O2 has the configuration I am telling, that sigma 1s and 1s, when they will combine, this gives you molecular orbital two type in the theory I have told. One is bonding molecular orbital, other is anti-bonding. So lower part in terms of energy is the lowest energy is bonding molecular orbital, it is anti-bonding molecular orbital. So 1s, two atomic orbital of 1s orbital will give you two molecular orbital. In my theory I told you what the number of atomic orbital will give you the number of the molecular orbital. Atomic orbital 1s, two atomic orbital will give you the two molecular orbital, and the type of the molecular orbital sigma 1s and sigma star means anti-bonding and anti-bonding molecular orbital. In the same way, these two atomic orbital of two atoms will twice as when they will combine, that will give you two molecular orbital. One is bonding lower energy and other is anti-bonding twice as, bonding twice as, anti-bonding twice as. And in when twice p and twice p, the electron will combine the atomic orbital, these two atomic orbital of twice and twice, twice s, twice p and twice p combines, that gives rise you the type of the bonding and anti-bonding as the fact lies here. The fact lies here. Here, if it is atomic number is more than 7, I will show you the trick. Without drawing the figure, you can draw the configuration. I will show you the trick. Don't get nervous. The fact lies here. So here I have shown you sigma 2pz. It is bonding molecular orbital out of p and p combination. The lowest part is sigma 2pz and above is pi 2py, pi 2px, or type 2px 2py, the same thing. So this is bonding, this is also bonding. This is sigma bonding and pi 2 part. It is sigma pi bonding. Am I right? And above this pi star anti-bonding, and pi star means anti-bonding, and the least one is sigma star. This is sigma bonding, the last one is sigma star. It always last one is sigma star. There is no change here. But if atomic number is less than or equal to 7, means from 7 onward, if you go on less than equal, if it is less than equal 7, then just you make the change, you pi 2px and pi 2py you make here, and in its place you take sigma 2pz above, you make interchange here, and all other things will remain the same. So this is the, say if there is oxygen, I am taking the example of oxygen. Atomic number of oxygen is 8, number of electron of 2 oxygen is equal to 8, 8 ja 2 ja 16 electron. So 1s, 2s, twice p, thrice s, thrice p means 1s2, 2s2, 2p, 4. It is the electronic configuration of the oxygen. Am I right? 8 electron. So 1s has 2 electron, you are writing 2 electron, and another oxygen has 2 electron. The 4 electron, this is arranged in Abba principle, increasing energy. An electron will be saved in Hund's rule and Paulus exclusion principle in accordance. I have already mentioned in the theory. So these 2 electrons, there are total how much electrons in atomic orbital? 1s and 4 electron. We will now put up 4 electron. So 2 electron here and 2 electron here. 4 electron filled up. Now go to twice s. Again 1s twice s. Here 2, here 2. So give here 1 here and another here, means pairing to the lower energy, electron will get paired up and remaining 2 will go up. Am I right? I have gone, I have, you can give here also, I have shown here. Am I right? So now problem with twice p. Twice p has 4 electron, singly fast. 1, 2, 3. Hund's rule. Then pairing start. So you can give here also. Am I right? So how much electron in the p orbital is 2, 2, 4, 4, 2, 8. 8 electrons. So you have to put first 2 electron here. Am I right? Lowest energy should filled up first. Then these 2 are of same energy. These 2 are of pi 2px, pi 2p are same energy, singly fast. Am I right? Out of 8 electron, I have put up 2. 1 here, 1 here. Another. How much? 1, 2, 3, 4, 5, 6. Remaining 2. So according to Hund's rule, singly fast. Then if electron remain excess in hand, pairing start. So you have to write the configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p2, pi 2px2, pi star 2p1, pi star 2px1, sigma star z0. No electron. This is the electron configuration. But if it is nitrogen, then just you make this above and these 2 below. Simple. So now you see how you what is the trick to write the electron configuration. Sometimes you make sigma 1s and sigma 1 star s kk. You need not to write it. If you write these 2 in the higher atomic orbital, atomic number, no need. These 2, 2, 2, 2, number of bonding minus number of anti-bonding. If plus 2 and minus 2, if you remove these 2, no matter. So sometimes it is kk, 1s 1 star equal to kk, because number of bonding and number, if you calculate number of bonding, so this is bonding, this is anti-bonding, this is bonding, this is bonding, this is bonding, this is bonding, and all star are anti-bonding. So from this you can find out number of bonding electron, number of anti-bonding electrons. So bond order equal to number of bonding minus anti-bonding divided by 2. You can find out the bond order. So I will show you later on. So how you to write the, either you write this or you may not write this too. Sigma 1s, sigma 1 star. You write this or may not write this. So the first thing you do, you at one line you write 5 sigma. If it is more than 7, Z is more than 7, 5 sigma in one, at a 1 by 1, sigma, 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 sigma. Then you write pi to pi star 2 and sigma. This is the technique. Pi to pi, pi, pi star, 2 pi star, then sigma. Now, if it is less than 7, mind that sigma, 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 5 sigma, you need not write to 5 sigma, you write 4 sigma. Sigma, 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 then I will do 1 is 1s, what is star, what is this, and that's later on. You write 4 sigma if it is less than 7. 1, 2, 3, 4. When you write 4 sigma, you have reduced 1 sigma from here. So in its place, you write pi. In place of 5 sigma, you have written 4 sigma, and in the 5th sigma, you write pi, pi. And what sigma you left out of 5 you have written 4, then that 5 should be go after pi and pi, 2 pi sigma, then again pi star sigma, just to make the difference here. You take this in its place and take this in its place, just make this arrangement. So without drawing the electronic configuration, you can write the electronic configuration. How I am showing you, this is oxygen, this is oxygen, am I right? So in exam, you may given oxygen this, you may given oxygen this, you may given oxygen this. In this way, you may be asked to write in increasing energy, bond order, bond length, peramenity, diameter, lot of things. So in all these cases, you need to know what? You need to know the molecular orbital. In terms of molecular orbital, you should know the writing of electronic configuration. So for oxygen, say it is oxygen is 7, it is more than 7, that is more than 7 means it is 8, am I right? It is 8 is more than 7, so 5 sigma, 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 1 is 1s, twice as, sigma 2pz, 1s, twice as, sigma, sigma star, sigma, sigma star, am I right? 1s, twice as, 2pz, 5, 1, 2, 3, 4, 5, and that sigma pi 1, sigma 2p1, sigma 2px, sigma 2py, sigma 2py, 1 is pi, 1 is pi star, sigma pi star, if it is greater than 7, am I right? So what the configuration, how to write the configuration? You see here 1s, we need 16 electron, 2 electron, 2 electron, 2 electron, so out of 16 we have got 2, 2, 2, 2, 8, 2 here, 2 here, 1, 2, 3, 4, 5, 6, 12. So now you see 12 electron has been filled up, you need 16, so 2 left, 13, 14, we have written already 14, 1, 2, 3, 4, 5, 1, 2, this is missed out, so we have written already 7, 2 means 14, we need 2. Now your main concept, without drawing the figure, you have to put 2 electrons, so here both are the same, you can't put here 2 alone because both are same, you put here 1, here 1, this is the style, no need to draw the configuration. So last electron you put in a beautiful way by calculated manner, number of bonding minus number of anti-bonding divided by 2. Now what is number of bonding? You may not include, you exclude this kk, or you can use, no matter, not change in the calculation. So how much bonding is there? This is bonding 2, this is bonding 2, 4, 6, 8. So bonding is 8. Now how much anti-bonding? 2, 3, 4. So bond order of oxygen is equal to 2. So we have calculated this one. Now you come to whether it is paramagnetic or diamagnetic. Answer, it is paramagnetic since there is unpaired electron. So the way of writing the configuration, you please write, if it is Z is equal to greater than 7, so 5 sigma in one line, one by one after one another, 5 sigma. One is 1s, 1s, 2s, 2s, sigma 2 pz, then pi, pi, pi star, pi star, pi sigma z star. And if it is less than 7, 4 sigma, 1s, 1s, twice s, twice s. Fifth in place, pi to px, pi to y. In the fifth place, you put sigma 2pz, then pi star, then last pi star, sigma star z. Am I right? So this is all about today's class regarding molecular orbital theory, and in my next class I will just go through the way with trick how to solve out all entrance exam solution. Please minutely follow the class. Thanks a lot for watching the class. You are once again requested to subscribe the class to remain updated for another practice set of entrance exam solution.